Okay, look, it's the stuff we've learned, written in kind of fancy calculus-y sorts of ways. Quick review. Gauss's law, we know that one pretty well, the way electric fields come sprouting out of charges and penetrate volume or surfaces, closed surfaces. And Coulomb's law that was associated, kind of the yin and the yang of this thing. You can like look at the holistic behavior or look at the build it up from little bits analytical behavior. Gauss's law for magnetism is a dud. Magnetic fields don't sprout out of anything. There are no magnetic monopoles. What magnetic fields do is described by Ampere's law. They wrap around stuff and form closed loops. I probably should do one of these little things. You can kind of do that with those two. You can do that, or we'll ask for surface. Anyway, you can wrap around something and see that there's a magnetic field circulating around a current or moving charge. And then there's the complementary Biot-Savart law, which is kind of analogous to Coulomb's and which figured out bit by bit. All right, so, look at this. I decided to add this in. This is something we never talked about. It's a weird technicality that's not too practical. But it turns out actually Ampere's law should include a term that involves the time rate of change of this. In other words, if the flux through a surface, electric flux through a surface is changing, it has this weird little thing where it induces some magnetic field. Okay, so what's missing? I think you can see. We've got the dAs and the dL and the E's and the B's. We're apparently missing. Yep, it must be E dot dL. We're missing that one. And it needs a name. What's it going to be equal to? Well, first of all, I'm going to tell you it's named after that wonderfully nice, poor English boy, Michael Faraday. Faraday is the guy who came up with the idea of the field concept in the first place because he didn't get to go to school much. He didn't know much math, so he tended to draw pictures. A lot of good stuff to tell about Faraday. But and I think I did a little bit. But in any case, this is going to be Faraday's law. What's it even about? Faraday's law. Well, what it's about is right here, this light's on. This light, it's using electricity probably generated by Georgia Power Company, and they've got a turbine somewhere with, maybe a nuclear plant, some combination of things, maybe a combustion turbine, maybe a dam, but something's spinning something. It's spinning some wire around in a magnetic field. It's a generator. I actually kind of have some of those in here. Wonderful. You should pull them out without losing things. No, they're in the box underneath this. I might get it out later. In any case, this is about generating electricity. How do you generate electricity? You change something. What do you change? Well, look, analogous to changing electric flux to produce a magnetic field, it turns out you can change magnetic flux to produce an electric field. You see, magnetic flux in itself doesn't do anything. Having a magnetic flux doesn't it's just sitting there. But if I change it with time, I get something interesting. So here it is. I'm going to go ahead and write it. The best way to write it to look calculus-y about it would be to say integral of B dA. And this term right here, this is, of course, the magnetic flux. It's measured in Tesla square meters. In Tesla square meters. And they decided to name that after someone. They named it after some Mr. Weber. So magnetic flux, the amount of magnetic field lines penetrating some kind of surface is the Weber. That's flux is the Weber. Now you might say, but it's zero. But I'm going to define my surface differently. I'm not going to define an entire closed surface. I'm going to define a surface simply bridging a gap in a loop of, say, wire. This is the context. If I have a, say, loop of wire, let me get all 3D about it. Yeah, like that. See, it's closer to you here. Magnetic field lines can certainly penetrate through that. Now, it might be that they loop around, and so I'll get zero, like this says. If I went all the way around, the field lines would leave it, and they poke back in, and you have a net zero. But they still can poke through some area. And this term right here says to take all the dot products of the little, take a little area. There's a little dA. It's got a little vector that represents it. The dot product of it and the field itself is maximized, you know, when the the field lines point straight through the thing. Kind of like the number of field lines that penetrate this loop. I'm picturing like you blow bubbles, soap bubbles, the little ring thing you blow through and it makes the bubbles. This is like the soap film getting penetrated by these lines. That's what magnetic flux is in a nice mathematical sort of way. And what I'm saying is, if you change magnetic flux, you cause some of this. Now, it's a little hard to maybe picture what's going on with the integral and the little path and everything, but just look at the units. Electric field is in newtons per coulomb, and I'm multiplying it times meters. Oh my gosh, we just made us some volts. We just generated an electric potential difference by changing a magnetic flux. Now the context is going to be something to talk about here, like which direction does a current flow because of this? It's going to produce an induced current, but we'll need to give specific examples, of course. So now that I've written all this fancy stuff up here, I'm going to erase it all. And I'm going to cut to the chase and get straight to an example. I'm going to start with the simplest example. It's a rod on rails. Look at this situation. Imagine you have a U-shaped, how long it wants to be. This is just some conductor, some wire, some metal, all like that. And we're going to put a bar laying across it. I think you get the 3D. This is closer, this is further off in the distance out there. And I need a magnetic field to poke through this thing so I can have a magnetic flux to change with time. Let me just poke field lines through it. Maybe they go everywhere actually, but they come through maybe pointing, I don't know, say up. And so there's some flux through here. Here's my soap bubbly film-like thing all through here, you know. And the question is, how much flux is that? Well, technically, it's integral of B dot dA. But what does that mean in a practical sense? Well, it means, first of all, you're going to multiply a magnetic field strength, B, times an area. And there's the area. So it's B times A. Well, is there anything else? Actually, I've got to be a little more generic. There's such a thing as having this not be just one length of wire. You could have it be a coil, a solenoid-like thing, or just a whole bunch of wire wrapped up. And every time you make another loop of wire, you give another surface for these field lines to penetrate. Like I don't know what a spiral soap bubble thing would look like. I'm not sure the analogy holds there. But in any case, I would multiply times the number of loops. And it also matters what angle it's sticking through at. If they stick through beautifully perpendicularly, like I'm trying to show here, you get the full effect. But if it's like slanted, you know, not much component go through, you don't get much. So that's why we have cosine theta here, where the theta is the angle between the normal to the surface, a little A vector, and the field. So here we do get the full effect when it's sticking straight out. That's easy to remember. I mean, NBA, I guess that usually means National Basketball Association. Anyway, so the flux is NBA cosine theta. And it's measured in Tesla square meters, which are Webers. That's some kind of popped up on this. So what does Faraday's law say? it says that E dot dl taken around a path is equal to the time rate of change of this. Now, E dot dl taken around a path, again, is an electric field times a distance, and that gives you Newton meters per coulomb. That's volts. That's some volts. And you know what those volts are like? Those volts are almost like that. These kind of volts. I mean, it's like a battery. It has an electromotive force. And so, in a practical sense, it's the EMF in volts that's going to equal ddt, the time rate of change, of NVA cosine theta. I had a fancy integral thing written earlier. This is where it gets practical. Rubber hits the road here. This is what we're talking about. Generally, when you generate electricity, you can have a number of loops embedded in a magnetic field, and you're either going to change the area or the angle. And when you change them, you make volts. Want proof that it's volts? Let's check. It doesn't have any units. This is Tesla, square meters, but it's per second. Dang, a Tesla is a Newton. Ooh, a Newton per ampere meter, if I'm remembering right. That's a Tesla. Square meter, we put seconds down here. Oh, God, I hope I'm doing this right. Yeah, Newton per ampere meter. Okay, this makes Newton meters. Okay, an ampere times the second. Oh, an ampere times the second is a coulomb per second times the second. That's a Newton meter. It's a volt. I told you. So yeah, you get volts out of this. So like, how many and what do they do? In this case, let's analyze this situation here. When I move this thing to the right, when I move this bar, just forcibly, just make it slide, hold it, I don't know, and I make it slide to the right at a speed v, then I apply this to this situation. What's changing? Is the number of loops changing? No, it's one. Is the magnetic field changing? Not that I told you, not in this example. What about the air? Yep, the area is changing. Now this is one, and this is one, and this is just B. So I'm talking now about this ddt NBA cosine theta being none other than B times dA dt, where A is the area. But look what the area consists of. It consists of this length right here, length, times this x. That's what the area is. The length is constant. You know, when you take a derivative, you can take the constant stuff out front. So this becomes, well, it does become B d Lx dt, but of course that's very quickly B L dx dt. Sorry, my writing's getting smaller, but you know what dx dt is. V, you gotta believe. If you want to make some volts with this thing, get a magnetic field going there, got some length, you slide that thing across, and the faster you go with it, the more volts you make. Believe. That was easy, wasn't it? This is what you call motional, not emotional, motional EMF, where you're actually moving something through a magnetic field and you're generating voltage. Now, what's interesting is the existence of this conductor, while crucial if you want a current to flow, is completely optional if all you want is a voltage. Because you could just like not have it and just make a bar fly through a magnetic field, disembodied out here. You know, that's just a figment of your imagination. And as this bar flies through a magnetic field, you know, I kind of want to, well, I think we can erase this now if you got it down. I would sort of like to show the top view, like what if I had a magnetic field? This is pointing out at you, let's say. You're looking down from up here. So the field points out at you. And basically I've got this bar moving this way through that magnetic field. The bar has a length, L. It's moving at a speed, V. I just made that already, and there's my B. And I'm supposed to get a voltage. What does it mean? It means there's an electric potential difference between one end and the other. which end's even positive anyway. Right-hand time, what I can do is I can take this V here, and I can take this B that points out, yeah, I got it. So my fingers come out of the board at me, my thumb is that way, pushed down. So it looks like positive charge, if there is some positive charge, it's going to get pushed to the bottom. Any negative charge is going to push to the top. And I'm going to have, obviously there's going to be an electric field in here. There's going to be a voltage. There's going to be a potential difference between this end and this end, where the positive charge gets preferentially pushed down here, negative charge up here. How about that? Oh, back to here. Which way would a current then flow? Well, if this were a battery, the positive terminal would be down here. I would hook up, I'd probably have a resistor, and I'd have a current flowing that way, like clockwise in this case. I think you can tell that if I reversed either the velocity or independently the direction of the field, I would also reverse that polarity and make my current flow, counterclockwise. So that's a way to make some electricity, make a current flow. In fact, you can give this a resistance R. And then the current that flows, if there is a wire, is going to be, E over R, which is going to be believe over R, right? That's how much current's going to flow. Gosh, you could probably find a power. The power would be, how about this? It'd be I squared R, that'll work. And I squared R would be B squared L squared B, that's a square, V squared over R squared times R. And all of a sudden I got B squared L squared V squared over R for a power. This is kind of neat. I'm making electricity. There's some other interesting things about this. Yeah, I think you know the context enough so I can erase this. I like to get mechanical about it a little bit. Let's see if I can pull this off the top of my head. I want to get mechanical about it. Let's say that I'm actually doing this with my hand. I'm pulling it. Does it like what I'm doing? Let's think about that. If I pull this thing to the right and a current starts to flow the way I said in this direction, look what I just did. I just produced a current this way in a magnetic field that points out at you. And we got this F equals ILV thing. Well, if I want to move it at a constant speed, I have to apply a force equal to that one, because that force, and which way does it point? Let's see, if I have a thumb pointing down in a, okay, my thumb points down, I got a, down, got out of the board, that's it. I get a force on this bar, a magnetic force on this bar this way. That's the magnetic force. This is the force, I don't know what name to give it, me. That's me. I have to balance that, so I have to do ILB. Wonder how powerful I am. Power mechanically is force times speed. Ooh, that's ILB times speed. And I is believe over R. Believe over R. That's I, right? Times belief. And that's B squared. That's the same expression for the, oh my gosh, it's the same expression. I just got the same expression for power using the mechanical idea of work being force times speed. I'm sorry, work being force times distance, but power being force times speed, is I did just purely electrically. Think about it some. That's kind of neat. Anyway, if you were taking this on an AP exam, I'll tell you they just love this problem on all AP exams. But it's magnetic, so it's not on this year's weird exam. But it sure wouldn't have been. I'd have been talking all about this. But let's talk a little more about it. You see, if you're going to DDT some NBA cosine theta to make some volts, we've only explored one of the things to DDT. We took care of that one. But what if we held the area constant? What else could we do? We could change the magnetic field. Yeah, you could have a given loop of wire, not changing size, not changing angle, none of that. And you could have a magnetic field through it. And if you had some way to control that magnetic field, like if you're making it yourself, you crank that magnetic field up and you'll be changing it with time. And it will cause apparently a voltage that will cause a current to flow around the loop. What direction? Like what if I had a loop of wire and had a field that pointed into the board everywhere, inside and out, but only the part inside counts. The only part that counts. And what if I make B increase with time? I get an increasing into the board flux here. Which way does it make the current flow? There's a way for me to contrive an answer to, like, pull something out of a hat here and actually show you how I could engineer the last problem to give the answer to this one. But actually it forms the perfect opportunity to introduce you to one of the hardest to put in words yet simple laws we've encountered. There's a law called Lenz's law. Lenz as in L-E-N-Z, and I'm going to put an apostrophe. Lenz's law. I'm not even going to try to write it. It takes too many words. Let me see if I can even say it. It probably comes out of my mouth differently almost every time I say it. Anyway, it's like this. The induced current is in such a direction as to oppose the change in the magnetic... The induced current is in such a direction as to produce a magnetic field opposed to the change in the magnetic field that produced it. That needs some examples, doesn't it? So here's the deal. If I increase the into the boardishness of this field, basically the world, the loop, gets all upset and says, we can't have this. What? Has it got a problem with into the board fields? No, it doesn't have any problem with into the board fields or out of the board fields. It has no preference between into the board and out of the board. It just doesn't like change. And it will do what it can direction-wise to oppose the change. The change is what's producing it, DDT, And so it doesn't mind there being an into the board field. It just doesn't, or flux. It just doesn't want it getting more into the board. So it's going to come up with, in a teleological, clever, anthropomorphized way, it's going to think about it and come up with a way to fight that. It is going to produce a current. I'll go ahead and say the direction. It's going to go this way. The current's going to spin that way. Here's why. Because if I do my fingers and thumb thing here like this, I'll find that to get an out of the board field in here, to fight the increasing into the boardedness, I need my thumb to point this way, and that's the current I have to get, because that current will make its own little field that points out, not to oppose the field itself, but to oppose the change in the field. To just make that clear, I'm going to reverse this. What if I still have an into the board flux, but it's decreasing because the magnetic field is decreasing? Then it gets upset in the opposite way. Again, it never had a problem with into the board flux. It just didn't want it changing. So when the into the board flux is decreasing, it does what it can to prop it back up. And so it goes the other way. wow. Lenz's law comes up with a bunch of sneaky stuff. That's a good example for now. Tell you what, let me show another motional EMF problem it's a classic. It's like this. What if you had a magnetic field into the board everywhere? Into the board everywhere. Except it doesn't go for, no, not everywhere. It's in a finite region. That's it. Okay, that's it. Yeah, and there's no field outside. That's our field. And we take a little loop of wire and drag it through the field. As this empty loop of wire enters the field and starts to get like into it a little bit, it starts to get an increasing into the board flux. Now that is bound to make the current flow, what's increasing into, I think that's going to make it go this way, isn't it? Yeah, it's like by the time it's part way in here, it's moving this direction. It's going to have, is that right? Okay, because it's increasing in, so make it go out by doing yes. So the current will flow this way. What about when the little loop is 100% completely embedded in the field? Oh, it's got a big field and big flux pointing into the board. Doesn't care, because it's not changing. So no current flows here. As it leaves, with what we've got a decreasing into the board flux, and it fights that with a little weird induced current that flows clockwise so that it can make some more into the boardedness to fight the change. In fact, actually, there's my little slogan. You got people who might protest one thing or the other. You might have left-wing, right-wing people, whatever. They might be protesting something, and they want to fight the status quo. Imagine a protester, make it like back in the 60s or something. Fight the change! These are people who don't care whether you're left or right or what the situation is. They just don't want it to change, and they'll fight it either way you change it. Revolutionary, right? Anyway, so that's kind of what Lenz's law is all about, fighting the change. Now, I told you I could engineer what we learned a few minutes ago to come up with the same answer. I certainly can in this case, because I could pretend that this little thing was a bar traveling into the thing. I could plant a positive charge on it, do my old first magnetic right-hand rule thing we ever learned. I could take a positive thing, put it in there, move it, this way, and up it goes. And yeah, I didn't need Lenz's law. I didn't really need it. But it agrees with what I just came up with my old right-hand rule. At least it agrees with it. Are there situations where it wouldn't be so clear? Okay, tell you what if the thing was already completely embedded in here? Yeah, how about this? What if it was already in here? Or it doesn't mind moving. In fact, did it stop on me?